Hello? Okay, good. So good morning all. I have to say I'm quite excited and super proud of what we'll be presenting today. And now our two companies, EDF and Sulzer, have partnered on this innovative technology, which is the additive manufacturing, for this ambitious target of getting the first pump impeller being manufactured by Additive being installed in a French nuclear power plant. I'm Boris Delmas, I'm head of strategic project at Sulzer, and I'm coordinating this specific project with EDF, and I'll be presenting with Mark and Yogi today. So if you
Yeah, hello everyone. So I'm Marc Delave from EDF at the Industrial Direction, and I am a project manager of a project which is industrialization of innovative manufacturing. And I'm very happy also to be here with Sulzer for such interesting innovation.
Hello, good afternoon, everybody. My name is Yogi Pardi. I am a global lead for additive manufacturing with expertise in material science as well. And I'm excited to be part of this talk today with Boris and Mark and going into a bit more details of how the technology works with you later on. So with that, hand over to Boris.
Thank you. Okay. So that's the agenda that we'll be following. So I will start introducing about the partnership that I was just mentioning earlier. And we'll be covering what is the strategy in regards with additive manufacturing. EDF will present what is its expectations in regard with additive manufacturing to use that technology into its nuclear power plants. And you will see that's a perfect match between the two. So that's how it ended naturally with that partnership. Then I will elaborate a little bit about how we've proven the concept, what is the approach which has been followed, which basically consists of demonstrating that both the mechanical properties and the chemical properties of those components manufactured by Additive are at least as good as the casted one. And then Mark will explain which are the future applications, which are the future components we intend to manufacture with that same technology. And we will have a Q&A session in the room which is just behind you. Okay, so just to now, so just to start a little bit with Sulzer. So I don't know if all of you know us. It may not be the case. So Sulzer is a Swiss company which is almost 200 years old, and we are active mainly in three kind of activities. So one is that we have a global leader. We are a global leader when it comes to pump manufacturing and pump services. We also offer OEM-like services on turbine and compressors and on motors and generators. And the third division is about static mixing, and polymer solutions. When it comes to the nuclear specifically, so we are one of the world leader when it comes to pump manufacturing in the nuclear industry. As you can see, we have more than 4,000 equipment running into the nuclear power plants globally, and mainly in the important systems, either for production or for safety. In France, that's more than 300 pumps which are running in the existing power plants. And recently, we have just been manufacturing and installing pumps related to the Grand Carénage project. Now we go a little bit into the technology by itself.
So, thank you, Boris. So, to begin with, within Sulzer, as Boris said, we are OEM of the pumps, but we don't just like to make new parts, but we would also like to repair and service components as well. And one of the leading technologies that we use for this is called laser metal deposition. And it's also known by other names like DED, for example. So the example here is shown that uses laser to melt the powder onto the substrate, which allows us to add very little amount of heat to melt the powder and create the new deposit. Because of that, we are able to repair parts that we previously never will have done, or deposit materials that are very difficult to deposit. Within Sulzer, we have in-house capabilities, but also we have qualified supply chain, and we operate to various various international standards. You know, you name it, ASME or ASTM or ISO, whichever is applicable in this case. So, with bearing that in mind, the basic technology that is used in the next step of the process here, what we call the hybrid additive manufacturing. Now, hybrid as a term is a combination of additive as well as subtractive. So in this case, what you're seeing here is an example of a 5-axis CNC machine with a interchangeable head where you can do additive as well as subtractive in the same equipment. And we're using this technology to manufacture pump impellers. And this is one of the breakthrough technologies, and Sulzer actually has patented this approach. What we do here is that we start with a forged billet or bar, as you see here in this picture. So initially what we do, if you look at the example shown here, we will 5-axis machine what we call the eye of an impeller, or the areas that we can machine as much as we can. But unfortunately, the tools are not bendy, so we can't go inside to machine it. What that means is then we use the additive tool within the machine to deposit the rest of the impeller outwards or radially in segments. So we put a small deposit on and then machine inside, and we keep doing that in a number of steps until we achieve the full diameter or the full geometry of the impeller. This approach allows us to have an impeller that is geometrically very highly conforming, but also is fully machined inside and out, which is rare because usually these impellers are cast and you cannot get tools inside the impeller to finish the internal hydraulic surfaces, meaning that it can impact the hydraulic efficiency. Also, if you're casting an impeller, often during the manufacturing process, the cores, the molds, or the patterns can move, and the geometry you achieve is not perfect. That impacts your performance and the consumption during the pump operation. So what this allows us to do is, because it's a fully automated process, it allows us to achieve a nearly close to perfect geometry inside and outside, and there's no human intervention between the process. So you press the button, once it's programmed, the finished impeller comes out of the single machine. Okay. Because of that, within Sulzer, this is our first choice of technology when it comes to impeller manufacture. It's not the only one. We still manufacture impeller by casting and other methods like fabrication. But in terms of quality and performance, this is the best way to manufacture, we believe, because in terms of process time, it is the shortest of all possible technologies that are available to manufacture a fully finished impeller. Okay? The best case lead time can be easily less than 3 weeks. Currently, it's 4 to 6 weeks. That's mainly because we are going through significant amount of development, regulatory qualification, and everything. And generally, if you compare to other additive manufacturing on 3D printing technologies, you can make much bigger parts using this approach. So that's why we are able to, well, we prefer this technology over other additive manufacturing technologies. So at this point, I'll hand over to Mark.
Yeah. So for EDF, I would like to present to you the reason why EDF is interested in innovative manufacturing. So it is not because it's new, it is not because it's innovation, but we are looking to have added value. So in fact, there is three mainly stream to added value, and the first one deal with lead time, the second with quality, and the last one with technical performance. So it's clear that the first one, innovative manufacturing, allows you to reduce your manufacturing time, and it's very interesting or for optimization of inventories. When you have a fleet of nuclear power plant as EDF, it's very interesting. And also for new project to be able to secure project planning. Because such innovative manufacturing, you can have a reduction by 3, sometimes more, of the delay, and it's very significant. The second item, quality, as it has been told, you've got the replicability, which is very interesting. When you have design one piece, you can do it for a series with the same quality. And a lot of manufacturing difficulty can also be, I would say, changed with reducing manufacturing steps. And also compared to forge parts, you can have a lot of homogeneity. And the last but not least item is to change design. So at first you can work here with ISO design, but for the last stream of added value, you can change your design, and it's something new. So it has to be think it over at the beginning of a conception. So you can move. Okay, thank you. So at EDF, just a short view of our organization. We have 2 projects. The first one is led by R&D and is focused on all the technical difficulty to remove. And the other project, led by industrial direction, is focused on industrialization. And to get to the industrialization with our supply chain, there are 4 principal conditions. So quite quickly, the first condition is to have a qualification methodology. So we are going to talk about it later. But we are also to define precisely the scope of relevant parts. And then we have also to address the fact that the sector of innovative manufacturing is not completely structured at the moment. And we need for powder suppliers, for machine suppliers, for suppliers which are able to manufacture for tier 1 suppliers, everything has to be structured. And then we have to be in EDF and outside EDF. Everybody has to be, I would say, confident that the fact that additive manufacturing is a key topic for the next year. And the project is focused on parts that we are going to install on nuclear power plants. And that's the reason why Boris, or maybe Yogi, I don't remember, is going to show the partnership. But the very interesting thing for us is to get to the installation on nuclear power plants. It's not just a demonstrator. It has to be through all EDF processes to be sure that all EDF engineering are okay to get this part installed.
Okay, so that's how the project started, and that's again the ambition that we've set, that we wanted to have the first impeller made by additive manufacturing being installed in a French nuclear power plant. And so what we've done is that we've selected an impeller which is from the conventional islands, so that's less, let's say, requirements when it comes to standard and code and everything, so not with RCCM being applicable. And so we've then manufactured a prototype which was tested both on mechanical and chemical properties by EDF. And from that, again, Yogi will make a deep dive into how good those performance, those characteristics are. And with the support of EDF R&D, then we got that impeller being tested. And after that, it was concluded that, again, the mechanical properties and the chemical properties are as good as the cast component. And we got a green light to go with the first of a kind. So the first of a kind is now manufactured, and it will be installed in Cattenom early next year. So it means that by end of the second semester, end of the first semester, sorry, we should have the first impeller running in a nuclear power plant. So that's, I think, a great success. So for you, Yogi, please to develop. No, sorry, that's you, Mark. Excuse me.
Just to focus on the characterization and validation of the impeller. So clearly the objective was to demonstrate that all chemical and mechanical characteristics are going to be equivalent to a cast impeller. So the standard we have reached is 10,213. And all the work of characterization has been done by EDF at R&D laboratories. So it's about chemical, mechanical, but also metallographies or micro hardness, and also 3D scan. And with all the result of this characterization test, with a lot of stencil and Sharpie test, and based also on Sulzer specification that have been reviewed by EDF, we can we can validate the fact that the installation is okay on for the first of a kind on a nuclear power plant. So what was important for us was to go through all this item to be completely sure, and it's not only just a part of EDF, it's different EDF engineering that brings together to the fact that it could be validated and installed. That's very important to have a team for us to be completely sure of the capacity of installation.
Okay. So, by the way, those who are wondering what the picture is showing is just the amount of extensive work that Mark and his team has done to basically completely destroy the impeller to gain the confidence, basically, and do all the testing. So that's what the picture is showing.
A quarter of, just a quarter of the impeller.
Yeah, a quarter of the impeller. Everything else has been tested. So the extensive amount of testing that is required to introduce such new technologies is vast. And what the next slide actually is showing is that before it was actually sectioned, some of the benefits that can be realized for such hybrid impellers include, for example, as I mentioned, the core of the impeller, which is the eye portion, is fully milled. Means that you have ideal alignment with the inlet flow, reducing potential for failures like cavitation. It's also, because it's a fully machined part, the amount of balancing required is none or negligible. The impellers we made to date have always come out fully balanced. What that means is that when you normally cast an impeller, as I said earlier, they tend to move during casting process, and when they come out, they're not really balanced. You have to remove material in certain places to make it dynamically balancing. This process gives you ready impeller to be used, okay? Also, in terms of direction of deposits, if you get a chance to come and see later, you will see that they align with the direction of the flow, giving you the optimal geometry. You also get a machine radii at the vane tips. That means that there's a better chance of impeller surviving high loads during its operation, okay? And fully milled hydraulic passageways means that internals are fully finished. That means that you're consuming less power and obtaining higher efficiency for the pump. So as we spoke, just some of the snapshot of what was done on these impellers. So earlier we talked about what you get in terms of better quality, and here is an example. So this is the what we call the ultra high cycle fatigue regime for the material. Each test sometimes can take a month to finish. And when we did these tests on a cast and hybrid material, we can see 33% or 1/3 increase in fatigue limit. And that's a significant amount of increase for, and also a confidence for a material that goes in a critical application like nuclear. What we also observed is when we do like-for-like test in a pump, we can also see increase in efficiency, and that's mainly down to the perfect geometry we are able to achieve using the hybrid additive manufacturing technology. Okay, so for future application,
Yeah,
Mark?
for future application, then up. So for the next stage, the next move, the first thing is that between EDF and Sulzer, we are looking to address an impeller now not only non-classified, but a classified impeller with safety requirements, and the requirements are going to be on the ASCEND code RTCM. So to this next step, we have to define precisely qualification methodology, and Additive is not going to do this alone or not only with Sulzer. So first, there are R&D projects as Nucobam or Arcan who are working on such topic. So it's going to be input for our work, but to achieve the goal, we really want to work with manufacturers already involved in innovative manufacturing. And it is Sulzer, obviously, but it's also Volant, it's also Emerson, Framatome. So it's a group where every manufacturer is really already involved. And we have the support of CETIM and CEA to get the project to have to define really qualification methodology for four processes. So laser powder bed fusion, laser metal deposition, wire arc additive manufacturing, and hot isostatic pressing. And on the planning, to talk planning, the aim of this collaboration is clearly to have by the end of 2024 the methodology operational, and then to be able to share to bring to the supply chain at the beginning of 25. And after, all this qualification methodology are going to be codified in ASCEND code. So the edition we are looking for is 26. This edition is going to be edited at beginning of 27. But the most important thing of the workshop, of the work, is to beginning of 25 to be able to share and to bring to supply chain qualification methodology for the four processes addressed. So that's the end of the presentation.
Yeah, so that's what we wanted to share with you. So I hope you have plenty of questions. If it is the case, we'll be happy to take these. So that's a small room over there. That, again, we'll be happy to take your questions. So many thanks and have a good day.
Thank you.